All right, so where are we going? What's our roadmap for the rest of the course? We go back to our original outline. We're going to spend a couple of lectures talking about stability, two perspectives of stability: input-output stability, as well as state stability. So based on the, so the first, which we'll start with, is just based on the input-output response, and the second goes into the internal states, how those state trajectories vary over time, because those may not appear in the input-output response. So we'll start by taking a look at that. And as you saw, I have a homework 6, which is posted and is due next Thursday. There's a couple of, well, they're basically of this, diagonalization of Jordan form functions of a matrix. There's no problems on that. Okay, so let's go back to where we were. We finished last day kind of right in the last part of this proof, and we were recalling our diagonalization, and we were recalling when there were n linearly independent eigenvectors, then we decomposed Cn into the direct sum of the null space of A minus lambda 1I. We didn't need these multiplicities that came from the minimum polynomial. And so what we're proving now in the case in which we have strictly less than n eigenvectors, so we don't have as many eigenvectors as we do the dimension of the system, that in order to form a basis for Cn using the structure of what we call these eigenspaces. So eigenvectors in general are in the null space of A minus lambda 1I, but in some cases we can't get, there may be repeated values of lambda 1, and we don't have as many eigenvectors as there are repeated values. And that's when it leads to this case of strictly less than n eigenvectors. Okay, so we were basically proving that we can make up a basis for Cn by studying the null space of A minus lambda I to the mi. Okay, so let's take a look at that. So what we proved last day, we defined this, we defined A invariant subspaces, we defined the direct sum, and so to prove that this space is the direct sum, there were two things that we have to prove. The first is that if you take any vector in Cn, that it can be written as the sum of component vectors where each of the component vectors belongs to each of these spaces. So x1 is in this space, x2 is in this space, etc., up to x sigma being in this space. But moreover, for direct sum, that decomposition into xi's, the sum of xi's, has to be unique. So there's only one way to decompose it. Right? That's the definition of direct sum. And so we proved last day that any vector in Cn, x, can be written as the sum of those components in the individual null spaces. And we were just starting to prove uniqueness of that decomposition. So let's just complete that now. And we're going to do that by contradiction. So to establish the contradiction, we're going to suppose that there exists a second set of vectors, v1, v2 up to v sigma, such that vi is in the corresponding null space of A minus lambda I to the mi. And that they sum up to 0. And that we ended last day by saying, if we can establish, if this were true, so if this were true, then if we just add this equation to this equation, we get that x is equal to, and so now you see the contradiction, or you see what contradicts direct sum, because now we have a second decomposition that works, x sigma plus b sigma. The fact that these add up to 0 means I still get x on the left-hand side here, but now I have, and this component is in this first space, A minus lambda 1I to the mi, etc. Okay, so if this were true, then we would not have a unique decomposition. So, and these vi's are not all 0. All right, so now let's let's work with this. So suppose we did have this situation
only
here.
if argument. It goes both ways.
Sorry?
I mean, it goes both ways. It's an only if argument.
It goes both ways.
Yeah. Because if you have two different representations, then you can have a zero vector, and then you can add it back on. So it's an if and only if.
What do you mean? That if you
If I have another vector that gives me that same vector in C, sorry, another set, the difference of that is a non-trivial zero, and then goes back to the argument. So it's an if and only if.
Yeah. All right. So now let's work with this and see where the contradiction comes up. Okay, so as we do with these types of proofs, you've seen a couple of these before. Without loss of generality, let's assume that it's the V1 that's not equal to 0. So without loss of generality, assume V1 is the one that's not equal to 0. Just to remind myself to stay off the very right side of this board, although it seems like nobody's taken the invisible, the seat where you can't see that part of the board. And so V1 is not equal to 0, so I'm going to write V1 just from that as minus V2 minus V3 minus V sigma. And then I'm going to take, you've seen this technique before in a proof that we did last day or the day before. I'm going to take that V1 and I'm going to pre-multiply by the matrix product A minus lambda 2 I to the M2. A minus lambda 3I to the M3, all the way up to A minus lambda sigma I to the M sigma. So I'm going to multiply that by, I'm going to pre-multiply V1 by that expression. Okay. And so I'm going to replace, I won't rewrite it, I'm just going to replace V1 with minus V2 minus V3 minus V sigma. And then I look at that, powers of A commute, right? So now V2 is in the null space of this matrix. V3 is in the null space of this matrix. V sigma, etc. is in the null space of this matrix. So if you multiply that out, that's equal to 0. Now, this thing here, if we go back to our, the first part of this proof last day, that's what we called P1 hat of A. Okay, it's basically the minimum polynomial with the lambda 1 term removed, evaluated at A. Okay, that's just from our notation last day. So that's P1 hat of A times V1 is equal to 0. All right, so now we've established this is, if this were indeed true, then this has to be true. Okay, so now if we look at P1 hat of S, P1 hat of S, again, minimum polynomial with the lambda 1 term removed. And we look at that term that we've removed, which is S minus lambda 1 to the M1. So that's just the term that we've removed from the minimum polynomial to get P1 hat of S. Those two terms, they don't share any common factors. So they don't disappear, they don't go to 0 at the same values of S, just by definition. We call that coprime, our coprime. They're coprime polynomials. What does that mean? It means that they don't share any common factors. I mean, what that means is that they don't disappear, they don't go to 0 at the same values of S. So if you know that two polynomials are coprime, then you could take any non-zero polynomials, h1 and h2, h1 hat and h2 hat of s. And I can write the following. So p1, h1 hat of s times p1 hat of s plus h2 hat of s, s minus lambda 1 to the m1 is equal to 1. Okay, so what that's saying is, I should write this properly, therefore there exists polynomials hi hat of s not equal to the zero polynomial such that this is true. That's a consequence of them being co-prime. So by the fact that these two polynomials are co-prime, the existence of these polynomials multiplied in this way by the co-prime polynomials, so that you get one on the right-hand side, is basically what it's saying in mathematics is that, you know, if p1 hat of s and s minus lambda 1 to the m1, if they had any common factors, then those common factors would show up on the right-hand side. You'd never be able to get a 1 on the right-hand side. So the fact that these two polynomials do not share any common factors means that there exist polynomials h1 and h2 such that you can get that identity. And now we can derive the contradiction of that. So therefore, if you plug in a, h1 hat of a, p1 hat of a, I'm going to evaluate it at a, this polynomial at a, and I'm also going to multiply both sides by v1 here. Plus h2 hat of a minus lambda 1I to the m1, v1 is equal to v1. Okay, and this is equal to 0 by what we've just established. This is equal to 0 by definition of v1, and then I have something that I've assumed to be non-zero. Okay, so I get, you know, v1 is equal to 0. So that establishes the contradiction.
At the beginning of, or sorry, at the end of last class, we wrote like this, like we wrote that we wrote that v1 equals.
We wrote this equation, right?
Right, but we also wrote like this x equals the sum of these little like x pieces and then
This
0 equals
piece of it. Yeah.
Right, and then we wrote like the 0 vector equals v of that, and we summed them together and then talked about that. So then, is this another way to look at it?
No, it's just following on from that same point. So let's go through the logic again. So to establish the uniqueness, so basically I'm going to try to say that there's no other decomposition of x in this way where each of these components belongs to these null spaces, which gives me x. And I'm going to prove that. So that's what I mean by uniqueness. And I'm going to prove it by decomposition. But to sort of get me started in proving that, I'm going to say, well, if this were true, then that's equivalent, as Dean pointed out, to saying that the decomposition isn't unique. Because if this were true, then I can get this equation. And you see, now I've got two different decompositions. All right? So that gets me started. But now I'm going to go further. So this is kind of where we left off last day. And now we said, okay, well, so basically I'm going to, you know, replace my uniqueness or non-uniqueness with this assumption, and then I'm going to show how that's violated. So that's the logic of that. Okay, good. The other thing that we should establish is that the dimension, and I'm not going to prove this, I have the reference to the text where it is proved, but the dimension of each of these null spaces corresponds to the multiplicity of that eigenvalue in the characteristic polynomial. Right? That was, you know, let's just recall. So characteristic polynomial chi hat a of s is equal to s minus lambda 1 to the d1, s minus lambda 2 to the d2, all the way up to s minus lambda sigma to the d sigma. And then, you know, the minimum polynomial is the polynomial of least degree, which evaluates to 0 on A. And we proved last day that it has to have this form, where it's got all the same factors as, oops, that's a 2. It's got all the same factors as the characteristic polynomial. It's just that the multiplicities, these mi's, are less than or equal to the di's. All right, so this is the multiplicity of lambda I in the minimum polynomial. That's the multiplicity of lambda I in the characteristic polynomial. Okay, so this is this space here, the null space of A minus lambda 1 I to the M1 has dimension D1. Dimension. This has dimension D2. This has dimension D sigma. And that makes sense because we've defined this D1 plus D2 plus D sigma is equal to N. All right, so let's actually say, let's define something for the minimum polynomial. M1 plus M2 plus M sigma is equal to M, which is less than or equal to N. Okay, and I'm not going to prove that dimension. It's kind of detailed. We've already done a detailed proof. I think that's enough. You can go to the text and see that. Okay, so we've got to the point where we've got a basis for the space of eigenvectors here, or not the space of I call it the eigenstructure. So we don't have n eigenvectors, but we know that the eigenvectors that we have can form a partial basis for Cn, and we have to complete that basis. How do we complete that basis in a way that allows us to get a Jordan form? That's where we are now. When we had n eigenvectors, we used those eigenvectors as columns of our similarity transform to get diagonal form. What should those columns be now? That's what we're asking. All right, so are there any questions about where we are, what this is, this proof? All right, so let's make ourselves more concrete now. I think this goes over a little more nicely if we start this with a concrete example. So the question that we're asking is, in case 2, so let me just sort of summarize where we are. In case 2, we have strictly less than n eigenvectors. I should say the matrix A has strictly less than n eigenvectors. Sorry. Eigenvectors. How should we complete this set of eigenvectors to give a basis for Cn? Well, this gives us a guide here. All right, so this tells us that if we choose the vectors, so we know that the eigenvectors are in this, but there's less than n. But if we choose the additional vectors to complete the basis in these null spaces, then we know we're going to get back to Cn. We know we can form a basis for Cn. But how do we choose them in a way to get a nice Jordan form? Furthermore, we'd like to choose these additional basis vectors. By additional, I mean the ones beyond the actual eigenvectors, to get a, quote, nice, quote, close to diagonal form for A. All right, so that's where we are now. So we're gonna approach this by means of an example. All right, so suppose you're given a characteristic polynomial and you're given a minimum polynomial. So in this case, suppose you had a matrix A, and we're gonna, in this example that's in the notes, A is a 6x6 matrix. Suppose it only has one eigenvalue at lambda, and its characteristic polynomial is s minus lambda, what did I say it was? Yeah, it's going to be 6. It's only one eigenvalue. And its minimum polynomial is s minus lambda to the 3. Last day when I was giving you some concrete examples, I said that indicates the size of the largest Jordan block. All right, and I left that hanging. And somebody came up after class and said, how do we know that? And so now this is what we're going to look at now. We're going to try to prove this now. Okay, so here in our examples, there's only one lambda. So there's only one eigenvalue. Well, there's one non-repeated eigenvalue. One non-repeated eigenvalue at lambda. And the multiplicity in the characteristic polynomial, we call that D1, is 6, and the multiplicity of it in the minimum polynomial, we'll call that M1 is 3. All right, so that's the data that we're given in this example. So there are different possibilities. That's not enough information to completely determine what the Jordan form is. So let's put a little bit more structure on this example. Assume in this example that A has 3 eigenvectors. E1, E2, and E3, associated to this eigenvalue at lambda. So we somehow have to come up with an additional 3 vectors to complete the basis of Cn. By the way, what's the dimension of Cn? Cn. What's the dimension of this as a vector space?
2n, 2n. Depends on the.
What a great question. It depends on what? It depends on the field. Thank you. So if I chose Cn C, what's the dimension of that? N, right. But if I chose Cn R,
2n.
2n. Yeah, good. Okay, so just make sure, so this is dimension n, this is dimension 2n. Okay, go back and take a look at that. So we're operating over the field C, right? Our eigenvalues are complex numbers. So this has dimension n. So I'm looking for n eigenvectors. They're complex vectors. That was a good question. Who asked that? You asked that, right, Dennis? In office hours the other day. Yeah. Okay, so in this example, assume that A has 3 eigenvectors, E1, E2, and E3. So that tells us that if we just look at the null space of A minus lambda I, that is dimension 3. So it's the span, remember what span is, it's the span of these vectors E1, E2, and E3. Suppose that, so let's just assume, so we still need a little more information. Assume that I'm going to write it this way. Assume that the null space of A minus lambda I squared is the span of, so suppose that has, let me write it this way first. Assume that the null space of A minus lambda I squared has dimension 5. And so I'm going to write the null space of A minus lambda I as the span of, now what 3 vectors do I already know are in that null space of A minus lambda I squared? E1, E2, and E3. They're in the null space of A minus lambda I, so they have to be in the null space of A minus lambda I squared. Okay, so I'm going to write it as E1, E2, and E3, and there's 5 of them. So I'm going to define 2 more vectors, and I'll call them V1 and V2 to be defined. And assume that we actually know now, because the minimum polynomial is s minus lambda to the 3, but assume that the null space of A minus lambda I cubed has, actually we don't have to assume this, we're given by the data. We know from our multiplicity M1 that the null space of A minus lambda I cubed has dimension 6. Alright, because this is the polynomial of least degree such that when you evaluate it at A, that is equal to 0. So that means A minus lambda I cubed is equal to 0. Okay, which means it's the 0 matrix, which means that its null space has to have the complete dimension 6. Alright, so that gives us well, we talked about this the other day, this is sort of giving us a clue to where we're going. That gives us the size of the largest Jordan block. Here, here there's only one eigenvalue, but we can have different patterns of Jordan blocks in this. But now with this data, we have it fixed. We know what the Jordan block is going to be. So let's see why that's so. So now I'm going to write the null space of A minus lambda I cubed as the span of, and what 5 vectors do I already know are in that null space? The 5 vectors in the null space of A minus lambda I squared. They have to be in the null space of A minus lambda I cubed. So E1, E2, E3, V1, V2, and I'm just going to call the last one W1. Alright, so I've got 6 vectors. So what are V1, V2, and W1? That's kind of what I'm asking over here. We'd like to choose these additional basis vectors to get a nice or close to diagonal form for A, which we're going to call the Jordan form. Okay, so choose. Why don't we choose V1, V2, and W1? Select V1 and V2 to be linearly independent solutions of, so we know that they're in the null space of A minus lambda I squared. Alright, so we know that, so let's just write this to the side. We know that A minus lambda I squared V is equal to 0, but I'm going to select them carefully. I'm going to choose them to be linearly independent, so V1 and V2 are linearly independent solutions of A minus lambda I V is equal to E1, E2, E3. So by what I've said over there, I know that there are 2 linearly independent solutions to those equations. So what have I done? I've set the right-hand side to the 3 eigenvectors. All right, so if you multiply both sides of that equation, of any of these 3 equations, by A minus lambda I, you'll see that the V is indeed in the null space of A minus lambda I squared, right? Because by pre-multiplication by A minus lambda I, the right-hand sides go to 0. But that you can always choose the VI's in this way is just a simple result of the fact that 0, so I'm going to rewrite that equation here, is A minus lambda I squared V which is the same as A minus lambda I times A minus lambda I V. All right? So that I can always choose. I'm basically going to say then that that's in E1, E2, and E3, right? That I can always choose the V to solve this equation. These equations result basically from this decomposition, or this point of view here.
I believe in different linear algebra class, we noticed that this approach, which is taking pre-images of A minus lambda I from the very shallowest eigenvectors, doesn't always work. Because sometimes you can choose eigenvectors that are rotated in a somewhat wrong way, that they have no pre-images under A minus lambda I.
So that there, if we've got this structure here, so remember I've set up the structure, that you can always choose two linearly independent solutions to these equations is always true.
We learned that you had to start from the very deepest layer and then find something that satisfies this but not this. Okay.
But you have to guarantee that they're linear. So I'm saying that you have to guarantee that they're linearly independent, right? So it may be here that you know, I mean I'm not going to find three solutions here, but I know that there do exist two solutions to those three equations. So there's some computational solving that has to be done, but all I'm saying is that exists. And the V1 and V2 that I find have to satisfy, at least they have to satisfy these two equations, or two of these three equations. Why don't we check with this, you and I, and we'll come back to it. So I'm just solving. I require V to be in this null space, but I'm going to pinpoint the V's I want by solving these three equations for V1 and V2. So it's again, there's three equations, and I have in my example two solutions. So let's just say without loss of generality, I'm going to, what did I do in the lecture notes? I'm going to assume that it's E1 and E2. Assume that V1 solves A minus lambda I to the V1 is equal to E1, and V2 solves A minus lambda I V2 is equal to E2. Okay, it doesn't matter, but they're going to solve, the V1 and V2 are going to solve two of these equations. And then I repeat the process. So now I've got 5 vectors. They're linearly independent from each other. And moreover, I have a particular structure for V1 and V2. And now I'm going to go to the last step, which is to solve for W1. And I think you can see what's coming now. We're going to select W1 to solve, and it's going to solve either, so I'm going to write it over on this part of the board, to solve A minus lambda I. So we know that W solves Q, solves this equation here, because it's in that null space. But I'm going to choose the W1 such that A minus lambda I W is equal to V1. So it's going to solve either of these equations. It's equal to V2. Okay, so I've gone one step further. And so, what did we do in the notes? So, without loss of generality, let's suppose it solves, what's the solution? Let's suppose that W1 solves this one. Okay, so now I've got W1, let's write it as W1, which is in the null space of A minus lambda I cubed such that it solves this equation here. And again, that I can always do this follows from a similar decomposition that I did for solving the V1s and V2s. So let's take a look now at the structure that we have. We've got this breakdown in terms of the eigenspace, the vectors that span the null space of A minus lambda I cubed. And from the equations that I've written over on the left-hand board, I know that, let's just rewrite our eigenvector equations. So let's just take the first three equations and rewrite them as AE1 is equal to lambda E1, AE2 is equal to lambda E2, and AE3 is equal to lambda E3. Now E1 and E2, they branch off, or I can develop branches from E1 and E2 to solve for V1 and V2. So I further know that A V1, so I'm going to rewrite this equation now. A V1 is equal to lambda V1 plus E1, and A V2 is equal to lambda V2 plus E2. And then finally, the equation for W branches off from this one. A W1 is equal to lambda W1 plus V1. All right, and that's just by the choice of V1, V2, and W1. Okay, so now if I take the similarity form structure that we're familiar with from the diagonalization, where, in the case that A was diagonalizable, we post-multiplied by some invertible matrix. I'll just adhere to the notes here. I call that invertible matrix T inverse. And that gave me, or that gave us, where we chose the columns of T inverse to be the eigenvectors of the matrix A, that gave us a form which was a diagonal, which was the matrix T inverse again times the diagonal matrix. So we expect to get a similar thing here. So that is, now instead of using the all eigenvectors now, I'm going to use the eigenvectors and these additional vectors. So I'm going to write it like this. So in terms of, I'm going to go across the rows in this chain, and the first column will be E1, the second column will be V1, and the third column will be W1. So V1 comes from E1 and W1 comes from V1. And I've ordered it in this way. It doesn't matter what order I do the rows, but I have to keep the row elements all together to be able to get the Jordan form. And the next row is, or the next column will be E2 followed by V2. And then finally I have just a single equation down here at the bottom, E3. Okay, so this is a 6 by 6 matrix whose columns are E1, V1, W1, E2, V2, E3. And now I take these equations and show that that's actually equal to E1, V1, W1, E2, V2, E3. Again, that same matrix which now I call T inverse. So I should put a little by definition here because it's by that equation that I'm defining what T inverse is. Times a matrix. In the diagonal case, or the diagonalizable case, this was a diagonal matrix. But now it's not going to be diagonal anymore, but it will be as simple as we can get. So AE1 is equal to lambda E1. So there's going to be a lambda up here. AV1 is equal to lambda V1 plus E1. And AW1 is lambda W1 plus V1. Okay, so that gives me that block there. AE2 is lambda E2. And then AV2 is lambda V2 plus E2. And then finally AE3 is just lambda E3. And then everything else is 0. So what you see here is the structure that we showed last day in our examples. In this case, we have 3 blocks. It's a block diagonal matrix, and there are 3 blocks. One is of size 3, one is of size 2, and one is of size 1. In this example, this is just an example. But you see now why we ordered the columns this way, so that we could get this nice structure here. This is not a diagonal matrix, of course, but it's an upper triangular matrix, so it's almost as nice, right? You know immediately how to compute the determinant of that, you know what its eigenvalues are just by looking at it. And it turns out that computing functions of that matrix can be done just almost as, well, a little more, almost as easy as the diagonalizable case. All right, so these are eigenvectors. We call these vectors here, so V1, V2, and W1 are called generalized eigenvectors. They're not eigenvectors, but they're kind of as close as you can get to eigenvectors without being eigenvectors, is kind of an informal way to put it. And they're just defined through these equations here. So you see the chaining is important, so that we get this, this upper triangular structure. And you can see some of these things coming through now. So we started with the characteristic polynomial told us, you know, what the eigenvalues are. It told us the dimension of the system. The minimum polynomial told us the size of the largest Jordan block. All right, so now if we see that Jordan form and we look at the null space, so as a fun exercise, just take that Jordan form and compute the null space of A minus lambda I cubed. So what do? You just take A, subtract all the lambdas from the diagonal and cube it, and you'll get the 0. Well, you'll get the fact that this is that matrix is 0, so it's going to have a complete null space, a 6-dimensional null space. Yes.
I just want to make sure I get the AT like congruent here. So it's AT inverse equals, and then that column, the columns there.
That's the matrix that I'm going to.
Okay, so there's inverse tens, and then the thing with the eigenvalues and all is TA T inverse. So then the T's cancel, and that's how you get these.
Yeah, so let's actually, good point, because I wanted to come back to that. But let's write it out like the way we did for the diagonal form. So I'm going to call it, instead of calling this matrix lambda for the diagonal case, I'll call it J for Jordan form. Jordan form. So it's kind of the simplest form of a matrix without being a diagonal matrix. And so what have we said here? We've said that AT inverse is equal to T inverse J. So now we have, we know these are linearly independent vectors, so we know that that's an invertible matrix. So now we know that A is equal to T inverse JT, or equivalently, J is equal to TA T inverse. So that's the similarity transform to put it into Jordan form. All right, so it's basically that similarity transform is completely defined by the eigenvectors and the generalized eigenvectors. Just like in the diagonalizable case, it was completely defined by the eigenvectors. So why is that nice? Well, looking ahead and thinking about what we did for diagonalization, we're thinking that, you know, that will provide us some ease in computing functions of a matrix A. Namely, if we can transform it to Jordan form, then if we knew the function evaluated on the Jordan form, we'd know the function evaluated on A, just like in the diagonal case. So, so now basically computing f of A for a function f is basically now boils down to computing f. Alright, because it's mod the similarity transform that we can deal with. And so the result that we will come to is the following. If J is, I'm just going to do one Jordan block here. So suppose you have a Jordan block, lambda, 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 and so all of the super diagonals here are 1, and everything else is 0. Then f of J is, it's an upper triangular matrix whose diagonal entries are just f of lambda, just like we saw in the diagonal case, f of lambda. And then the superdiagonal are f prime of lambda, so that means the derivative of f with respect to s, whatever its parameter is, evaluated at lambda, f prime of lambda. So f prime of s is equal to df by ds. And so f prime of lambda is f prime of s evaluated at s is equal to lambda. The super diagonal is f double prime at lambda over 2 factorial. All the way up to the corner element here, which is the n minus first derivative of f evaluated at lambda over n minus 1 factorial. We have to show this, but that's true. And then everything below is 0. So it's an upper triangular matrix. And then we can generalize this to, let's just write another kind of example. Suppose that we had a matrix which it wasn't just one Jordan block, you had a bunch of Jordan blocks. I've got these examples at the back of the lecture notes. But suppose this, so this was example, that was example 1, this is example 2. Suppose that, for example 2, I have eigenvalue at lambda 1, and there is a 3 by 3 Jordan block associated to that one. I'm going to write it like that. And then I had another Jordan block associated to lambda 1, and that was a 2 by 2 Jordan block. And then I had lambda 2, and I had a 2 by 2 Jordan block associated to lambda 2. And then I had just a 1 by 1 Jordan block associated to lambda 2. Okay, so again, I have a 6 by 6 matrix. It's got 2 eigenvalues, 3 at lambda 1 and 3. Oh, sorry, it's not 6 by 6. It's 5. It's an 8 by 8 matrix. Let's count properly. There's 5 eigenvalues at lambda 1, and there's 3 eigenvalues at lambda 2. And I have a 3 by 3 Jordan block, a 2 by 2 Jordan block, a 2 by 2 Jordan block, and a 1 by 1 Jordan block. Everything else is 0, and these are all zeros. So if I don't mark it, it's just 0. Then f of j is equal to, so we just sort of do this algorithm for each of the Jordan blocks. Right? It becomes, again, it's a block diagonal matrix where this is f of lambda 1, f of lambda 1, f of lambda 1, f prime of lambda 1, f prime of lambda 1, and up here in this corner is f double prime of lambda 1 over 2, 0, 0, 0. Sorry, that's not really nicely aligned, but that's my, that's the, the first block on the diagonal. And then I do that again here. So I just follow my rule for a general Jordan block. This is f of lambda 1, f of lambda 1, f primed of lambda 1, 0, etc. Just f of lambda 2. So I have a 2 by 2 Jordan block there, and everything else is 0. All right, so once you've got it into Jordan form, calculating a function of that matrix, and what are we always interested in? We're interested in the function which is the exponential to compute e to the at, or e to the jt in this case. You can just basically do it by inspection. Now, why is that true? So for the diagonal case, it was obvious. We just computed it directly. In general, to compute functions of a matrix, you can't. You have to look into that in a little more detail. So when the matrix is not diagonalizable, but it's of another form, including Jordan form, we need another way to compute the function of the matrix. And the method that we have here in the notes is called the method of interpolating polynomials. All right, so in the notes we have a proof of this. So let's go through that. And here's where I've got I've developed it a little differently or I will develop it a little differently on the board than I have in the notes, although it's the same method. Just because I found this is a bit of an easier way to explain this.
Which page is it in the notes?
It's right where it says functions of a matrix. So right where we left off, after eigenvector and generalized eigenvector chains, functions of a matrix. So it's right, yeah. Okay, so how to compute f of j? Or in general, I'm just going to write it as f of a in general. And in all of this, we're making some fairly lenient assumptions on the function f. So A is a square matrix. We're assuming it's in Rn by n. We're assuming that f is what we call an analytic function. So it's well behaved in a certain way. Okay, so maybe it's not fairly lenient, but it's assuming that f is well behaved. So what does it mean to be analytic? It means that the function itself is locally means at different values of s, locally around that. It's given by a converging power series. All right, so it locally looks like a polynomial function.
Could we relax this to the n derivatives existing?
Yeah, I think so, because you just need, you need to be able to compute as many derivatives as you need. So we usually say that just to be a little more general, but I don't think we need it. Yeah, so maybe to be a little more specific so that it works. Okay, so we're going to compute it by the method of interpolating polynomials. And basically, this method says that you can compute f of a by knowing what f is evaluated at the eigenvalues, what its derivatives are evaluated at the eigenvalues. All right, so it's that we're going to compute a function of a matrix by knowing properties of that function on the spectrum of the matrix A. And this is why it works. Okay, so let's just keep our characteristic polynomial and our minimum polynomial on the board up there. And let's go back to something that we presented a while ago, which was around the Cayley-Hamilton theorem. So we know that if we have two polynomials, P1 and P2, have, P1 hat of S and P2 hat of S, that we can divide those polynomials through by the minimum polynomial, and we get P1 hat of S is equal to Q1 hat of S psi hat A of S plus R1 of S, and P2 hat of S is equal to Q2 hat of S psi hat A of S plus R2 hat of S. Okay, that's just the quotient and the remainder. So I've divided each of those through by the minimum polynomial. We've also shown before that it's true that if P1 of A, or sorry, P1 hat of A is equal to P2 hat of A, then that's equivalent to saying that R1 hat of S is equal to R2 hat of S. All right, so if P1 hat of A equals P2 hat of A, then the remainder polynomials must be equal to each other. But it's also true in the other direction. All right, so you've seen this a couple of times before.
We have the hats everywhere because it's all in the...
Yeah, in fact, I've been using hats in the Laplace domain,
Yeah.
so I'm just maintaining that. So make sure you understand that. I'm going to say prove as an exercise. You know, this way I think is obvious, we've seen it, but prove the reverse direction. Okay, so then we know that if R1 is equal, let's go over here now. Sorry I keep going back and forth, it's not really well. Okay, let's erase everything except the characteristic polynomial and the minimum polynomial. So if we knew that R1 is equal to R2, then by just subtracting those two polynomials, P1 hat and P2 hat, we'd have that P1 hat of S minus P2 hat of S is Q1 hat of S minus Q2 hat of S times the minimum polynomial, psi hat A of S. All right, so you look at that. This is a polynomial, this is a polynomial, and that's a polynomial. But we know the form of the minimum polynomial, right? So that tells us something about, you know, where the zeros of P1 minus P2 are, because we know where the zeros of this polynomial are. So that tells us that I'm going to drop the S, and just, you know, I'm dropping S just for brevity here. P1 minus P2, you should understand there's an S there, has a 0 at, well, so since this appears on the right-hand side, we see that it has a 0 at lambda I of order at least mi. That's just because P1 hat minus P2 hat is some polynomial times another polynomial which we know has a 0 at lambda I of order at least mi, or of order mi. You may get another, you know, you may get another 0 here. Okay, so that's just by looking at that structure. So that gives us something called the spectral, well, actually let's write them out what they are and then we'll name them. That tells us, therefore, P1, and that indicates the Lth derivative. So the Lth derivative of P1 evaluated at lambda I is equal to the Lth derivative of P2 evaluated at lambda I for I equals 1 up to sigma. So it's going to happen for all of the lambda i's. And for L, so L is like an index, it's going to happen for L equals 0, for just P1 minus P2. It's going to happen for L equals 1, the first derivative of P1 and P2. L equals 2, all the way up to mi. All right, so for L equals 0, 1, up to mi, okay, mi minus 1, because it's got to be, because it's going to, if we take the mi's derivative, it'll disappear. Okay, so I'm just looking at that polynomial. So those should have hats. So this is what we call the spectral interpolation conditions. Or SIC. Alright, but we can also see that the spectral interpolation conditions imply that P1 hat of A is equal to P2 hat of A. So we're saying that if this is true, where lambda I are the eigenvalues of the matrix A, then you know that those two polynomials are equal on A. Now why is that true? So this is a theorem, or a lemma, it's probably a lemma, but we'll call it a theorem. So the proof of that is just look at P1 hat minus P2 hat, evaluated on lambda, all right, so this is my difference polynomial, evaluated at s is equal to lambda, is equal to some, I'm just going to call it some polynomial mu of lambda times the minimum polynomial, psi hat A evaluated at lambda, for some polynomial mu of lambda. And why do we know that? It's because P1 minus P2 has a 0 of order at least mi at lambda I. Okay, so then that tells us that therefore P1 hat of A minus P2 hat of A is equal to mu of A, minimum polynomial evaluated at A, which is equal to 0 by the definition of the minimum polynomial. Yeah.
Can you repeat again what you said by this, that first line is true? You said P1 minus P2 has a 0 of order.
Yeah, so I'm basically right, I'm just saying again what I know from up here. So because it has a 0 at lambda I of order at least mi, and that's true for lambda 1, lambda 2, up to lambda sigma, that's just captured here by the fact, I mean, I'm sort of going backwards, I'm capturing this by the fact that that polynomial has to be some other polynomial multiplied by something that looks like this, because that's exactly what this says here. Okay? So then, you know, evaluated at A by definition of the minimum polynomial, that tells me that these two functions of A are equal to each other. Yeah?
Why does the SIC hold?
If the SIC holds.
Oh, are we not proof of SIC?
So what we're saying is that, so I'm sort of saying it one way here. So if this is true, then this is true. But the reverse is, if the spectral interpolations condition, if the spectral interpolation conditions hold, then the two polynomials are equal to each other on A.
Or how do you know that SIC is true?
I'm just saying if they're true here. So this being true implies this being true. So I have to first of all come up with, you know, I want to, this isn't always true, of course, and I have to first of all establish that that's true before I can prove that this is true. Okay, so there's some work in establishing that, which we'll do. Question?
I don't see how you're actually using the interpolation conditions here. Like, you don't seem to actually be taking any derivatives. So.
No, I'm saying that if this is true, that's equivalent to saying that this is true,
oh,
right? Which is equivalent to saying that, you know, you're going to have something on the right-hand side of that form, which is what we call the minimum polynomial. Okay, so I'm kind of just stating the same thing in different ways.
Those p's on the second one is not before you define them to be that form.
These are the same p's. These are, I mean, I'm saying these p's
Yeah, but
are,
that's not the p's from the right-hand side, which are equal to some polynomial.
no, I'm just saying,
Just some two p's that
Yeah.
happen to agree on all the eigenvalues of.
yeah, but in fact, they are, you know, if, in all cases, the P1 minus P2 is gonna look like this. So it's, you know, P's can be of that form. But this holds for any two P's. But, you know, if the remainders are equal, then you know that the difference is gonna have that form. And then you know this is true. Okay, so the point here is that, let's sort of recall, maybe let's repeat what we just said, which kind of, you know, reinforces the two questions that were just asked. Hence, so let's write this down. Hence, if you have polynomials p1 hat and some other polynomial f hat, such that, so you just pull up two polynomials, but you know the spectral interpolation conditions hold on those two polynomials. So if you have that p1 hat elf derivative evaluated at lambda I is equal to f hat elf derivative evaluated at lambda I, and that's true for I equals 1 up to sigma, and L is equal to 0 up to mi minus 1, then f hat of A is equal to p1 hat of A. Right? So it kind of answers, kind of points to those two questions. So I just pulled out two polynomials, but if I know the spectral interpolation conditions hold, then I know that that polynomial evaluated, those two polynomials, or evaluated at, well actually, okay, so if p1 and f were both polynomials, then I know that if the spectral interpolation conditions hold, then I know that those two polynomials are equal on A. But even if f is not a polynomial, suppose p1 is a polynomial and f is just some analytic function, then I also know that this is true. Because, you know, f is, essentially it's because this is why we need f to have as many derivatives as we need. So, because f locally looks like a polynomial. So even if f is not equal to p1, but their spectral interpolation conditions hold, then you get that f evaluated at that matrix is the same as p evaluated at that matrix. And this is essentially what we use to compute functions of a matrix. We find convenient polynomials which have such that the spectral interpolation conditions hold with the function that we want to compute. And then we use this fact to be able to compute the function of a matrix. So let's go through that a little more carefully to show exactly how we do that. So suppose you're given f, or, you know, when I've written it as this not, but let's just suppose you're given a function of f and you want to compute f of a. Suppose you choose any polynomial p such that p hat of s is equal to a polynomial whose degree is the degree of the minimum polynomial. Okay, so it's a1, actually one less than, it's always m1 minus 1, so m minus 1. a1s to the m minus 1 plus a2s to the m minus 2 plus ams to the 0, where m is the degree of the minimum polynomial, and the ai's, so the coefficients ai are chosen such that the spectral interpolation conditions hold, are chosen to make p, the elf derivative of p evaluated at lambda I. So you have to know a, and given f, given a, and by n, you've got the eigenvalues of a. So the elf derivative this is an index, evaluated at lambda I is equal to the L derivative of f evaluated at lambda I. And this is for I equals 1 up to sigma, and for L equals 0 up to mi minus 1.
Professor, that A is not made up of those A's, right?
No, these are just coefficients, yeah.
Okay,
So those are different. This is our what we're given in the problem. We're given our n by n matrix. We're given a function, e to the, you want to compute e to the at. So your function is e to the st.
So I could have called these, right?
Yeah, we could have called them b's. I'll call them a's so I don't make a mistake, because I wrote my notes. So we choose that. So we choose p of the right degree such that the spectral interpolation conditions hold. Why are we choosing it so that the spectral interpolation conditions hold? Because we want f of a to be equal to p of a. So what does it mean if the AIs are chosen? So these coefficients are chosen to make the corresponding derivatives of p evaluated at lambda I to be equal to the corresponding derivatives of your given function evaluated at lambda I for those indices. It basically means that the AIs, this means the AIs are functions of, so once we've solved these equations for the I and the L indices, we'll find that that constrains these coefficients AI, and that they will be functions of f at lambda 1, f, the first derivative of f evaluated at lambda 1, the second derivative of f evaluated at lambda 1, all the way up to the m1 minus 1th derivative of f evaluated at lambda 1. And f evaluated at lambda 2, f first derivative evaluated at lambda 2, etc., all the way down to f evaluated at lambda sigma over to f to the m sigma minus first derivative evaluated at lambda sigma. Okay, so by, we've got our f, you know that. You choose a polynomial, you parameterize it by a, you choose the AI, you choose the AI such that these conditions hold. That's all computationally easy to do. That means that when you solve for the AIs, they're going to be functions of these terms here. That just comes from the spectral interpolation conditions. Okay, so then, once you've solved for the AIs, you're going to get a P of A, which looks like, so you've solved for the AI, this is going to be A1, A to the m minus 1 plus A2A to the m minus 2, all the way up to A to the mi. And then f of a will be p, or that should be p hat of a. And f of a, which is what we wanted in the first place, will be equal to p hat of a, as long as the AIs were chosen using these spectral interpolation conditions. All right, well, if we look at that, so I'm going to write it out as f of a. So what is f of a going to be? It's going to be the summation from I equals 1 to sigma, summation from L is equal to 0, from 0 to mi minus 1 of PIL, I'm going to call these coefficients here. So these are going to be functions, these are going to be polynomial functions in A that are, basically coming from these terms here. The powers of A, times, this comes from the spectral interpolation conditions, the L derivative of f evaluated at lambda I. All right, so all I've done is just develop the logic by choosing the AIs, by selecting the AIs such that this is, this condition holds. we're going to get, we'll be able to evaluate p hat of A. We know what the AIs are. And since f of A is equal to that, I'm just going to write f of A in that form. Now, the really cool thing here is that these polynomial functions of A are independent of f. Independent of f. They're polynomials in the matrix A. Polys in A. So those PILs can be computed independently of f. That form always holds. The PILs don't change if f changes. If f changes, what changes is this thing over here, which is easy to compute. So the PILs, hence these polynomials in A, the PILs can be computed independently of f. Can be computed. You still need to compute them with an f. But you can choose really simple functions f to compute those independently of f. So what am I going to say? It can be computed independently of f by choosing simple functions f1, f2, f3 that are easy to compute here, and easy to compute f of A, such that fi of A and fl to the lambda I are easy to compute. So do that, solve for the PILs, and once you've got the PILs, then you've got a general form of f of A. So I have an example, which will take probably 5 to 8 minutes to do. Are people willing to stay for another 5 to 8 minutes to do this? Or do you want to finish this now? Who wants to stay? Who wants to finish this now and go home? Who wants to stay? Who looks really dumbfounded that this is like crazy? We can do this on Tuesday. You now have the basic tools for computing functions of a matrix, because I told you what the answer is. But you don't actually, to compute f of j, like we did, I just gave you the answer for what f of a Jordan form looks like. You have to apply this kind of methodology, and that's what's done in the lecture notes. You can see the example in the lecture notes, and I have another example that we can work through. All right, so why don't we do that first thing on Tuesday, and then you'll be able to compute f of j.